Hello, we're Team 7 studying Burj era. This week, each team members did their research and study about trust, and Yu Song-ho also participated as a second presenter. Now let us begin our ninth presentation. Starting with a quick review about last week's material, we will move on to the episode and construction of diagonal truss and its connection. We will end our presentation with a short preview about what we will be studying next week.
Last week, we have focused on the wind load and how considering it is critical to highlight buildings like Burj Al Arab itself. Architecture Tom Light and structural engineer Anthony McCutter work on how to withstand this wind load sufficiently while maintaining the building's outstanding exterior. First solution they chose was to put exoskeleton layer leg along the building. It is made up of two legs each and 273 meters high. It is a structure that resists the wind load most directly. The second solution was the rail bracing frame at the front. The rail brace frame or the expand keeps the V-shaped core from parting. The building has three X-shaped structures in total. Constructing exoskeleton layer leg caused three problems. First, how to maintain perfect curve shape. Second, the thickness. Third, the corrosion. The curve shape was achieved by dividing the 270-meter long structure into 12-meter short segments. That way, it was more suitable for the constructor to achieve a flat curve shape as a yacht. The building standing at the shore of Dubai had to withstand strong sea wind. However, as the architect and the client wanted the building to look outstanding, they wanted the exoskeleton to be thin as possible. As such, the engineer designed the structure thin, causing the need to TMD afterwards for sufficiently stability. The corrosion of the steel structure was also considered. It was prevented by spraying corrosion prevention spray and supplementing the surface with additional steel plate. The 60-meter long layer brace frame was divided into three parts when constructing. The segments were lifted using the sub-crane placed at each wing of the core. These two structures were not sufficient in withstanding the wind load. This week, we will learn about additional structure for the wind load and how these structures were connected to the building.
We have learned that as the wind load increases as the height of the building increases, skyscrapers are exposed to hazards caused by wind. The Burj Al Arab tried to resist the wind load by installing exoskeleton. However, there was a problem. When the structure is composed of only horizontal and vertical members, it rotates easily and destructs because it cannot resist the moment at pin support. Therefore, additional members to resist this moment is needed, and that is the truss. Truss is triangular structure which stabilizes the structure by generating extra compression or tension. The exoskeleton we have installed in advance was not stable with only horizontal and vertical members present. In addition, structural engineers asserted the need of truss to the architect. This truss would create additional tensile stress to the exoskeleton, consequently helping the structure to not destruct. Installing them had two problems. One was about the design of the truss, and the other was about its transportation. First, about its design. The architect was very sensitive about the exosteel structures because it could affect the building's exterior. Therefore, the truss also had to be outstanding. He required it to be curved as the building and thin so as not to offend the hotel guests. Another problem was the transportation. The truss they were about to install was long and heavy. At first, the constructors wanted to divide the member into parts, transport them, and weld in the air. However, as the truss required high stability, unstably welding them in the air would probably lose the stability. Also, the heat of Dubai required them to consider thermal expansion. Perfectly fixing them with the exoskeleton would change the exterior later because of thermal expansion. As a result, the structural engineer decided to transport the truss in one part, and the chief contractor had to solve this problem. So, how did they solve these two problems? First, for the design and stability, the structural engineer offered 7 alternative solutions to the architect. Among those alternatives, the architect chose one structure that satisfied his taste. The truss was 85 meters tall and 165 tons heavy and arranged in a very curved manner. There are 3 trusses on each side of the building. To withstand a strong wind load, the truss consists of extra 8 trusses inside. For the prevention of corrosion, the surface was grit blasted using metallization's arc spray systems. The aluminum coating are expected to guarantee a 15 to 20 years protection against corrosion in the harsh coastal environment in which the Burj Al Arab stands. The design truss was manufactured in a one form 15 kilometers away from Burj Al Arab. As the truss was 12 meters long than the 73 meters long Airbus A380, the biggest airplane existing, transporting the truss was no easy work. The chief contractor brings in one of the world's largest heavy lift transporters, a beast with a total of 80 wheels. It made the slow journey to the construction site of an average speed around 6 kilometers per hour. How the truss was connected, there was also a problem. If a perfectly designed steel structure for wind loads fails to fully engage with the building, it will be like a statue erected in front of the building. As such, the connection between exoskeleton and the building is very important. This connection can be largely divided into 2 parts: the connection between the building and the exoskeleton, and between the exoskeleton and the spiral truss. Connecting the exoskeleton and the building was quite simple. To withstand wind loads that act directly on the building, the exoskeleton must be subjected to sufficient force in every part. Therefore, the connection is required where the most effective force can be dispersed when the load on the building is analyzed. The problem was the connection between the exoskeleton and the spiral truss. They could not simply weld the spiral truss with the structure because of the hot weather. Dubai has an average annual temperature of 30 degrees Celsius, a maximum temperature of 49 degrees Celsius, and a daily temperature difference of 14 degrees Celsius or higher. Therefore, in hot daylight, the steel structures expand, while at night it shrinks. When the 85 meters long steel structure was heated, it could expand up to 5 centimeters. 5 centimeters is a short length for normal people, but when strongly welded to the building, it could destroy the exoskeleton hardly. The chief contractor and the structural engineer had to consider thermal expansion at foremost. The connection between the building and the exoskeleton is divided into 2 parts. The first is the connection between the rear bracing and the exoskeleton, and the other is the connection between the core and the exoskeleton, which most directly resists the wind loads. The former part was connected by a girder of rear bracing frames straightly to deliver the lateral load of the building to the exoskeleton. For the latter part, the exoskeleton was connected directly with the core from the beginning. Connecting the truss to the exoskeleton was a trickier job. That was because it had to lift 165 tons of huge truss close to the weight of 16 express buses up to the point of support for its connection to the exoskeleton. The engineers considered dividing them into two segments for the safety and convenience of the job. However, because it could not be easily welded in the air, constructors decided to lift the whole truss in one piece. Lifting the truss was a hard work for the three tower cranes already installed at the site. Therefore, the chief contractor looked for a solution and brings in special lifting gear from Singapore. His team sets up winches like those used on offshore drilling rigs high on cantilever frames 15 meters from the building. Cables with a braking strength of 225 tons are attached to the end of the truss. The two massive winches take up the strain and then painstakingly raise the diagonal truss little by little up beside the building. The construction team were able to raise the truss to the appropriate height, but the question of how to connect them remained. To fluently solve the thermal expansion and shrinkage problem, the fixing bracket on the frame contained a vast washer which swivel until it lines up with the hole in the diagonal truss. Then the steel pin is inserted through both holes, locking them together. This device could adjust itself fluently by swiveling when expanded or shrunk. And the truss is now fixed securely in place. This connection between the main building, exoskeleton, and trusses serves to deliver the lateral load acting on the entire building, especially wind load, to the exoskeleton. However, withstanding the wind from the shore was not the only problem. The engineers had to solve a problem of vortex shedding in front of the building caused also by the wind. How they solved this, we will learn in our next presentation. Thank you for listening.